Something unusual just happened near Antarctica, and it involves two separate magnitude 6.0 earthquakes, striking almost exactly the same location within a 10-minute window of each other, not one, two, back to back. And the first reaction from anyone watching the seismic monitoring systems would be to assume there was a data error, some kind of glitch in the feed. But there was no glitch. Both events were real, both were recorded, and both happened along one of the most remote and least talked about plate boundaries on the entire planet. The location is the Western Indian Antarctic Ridge, a massive underwater mountain chain running through the Southern Ocean, sitting between the Antarctic plate and the broader Australian plate system. Most people have never heard of this ridge, and that makes complete sense, because it sits beneath one of the coldest, most isolated stretches of ocean on Earth. No major shipping lanes pass directly over it. No coastal cities sit near it. No viral footage is ever going to come out of a place like that, but geological importance has nothing to do with how many people are watching. This ridge is one of the most geologically active features on the planet, and what happened there today deserves a proper explanation. Both earthquakes struck at a shallow depth, roughly 6 miles below the seafloor, or about 10 kilometers. Both were approximately magnitude 6.0. The first hit at around 1451 UTC, and then about 10 minutes later, a second 6.0 struck close enough to the same location that on the USGS map, the two events appear as basically a single dot. That kind of event, two similarly sized earthquakes, close together in time, close together in space, has an actual name in seismology. It is called an earthquake doublet. It is not a common occurrence, and it raises an immediate question. Why did the same section of an underwater ridge rupture twice in the same 10-minute window? To understand what is happening here, the geology of this specific location matters a lot. The Western Indian Antarctic Ridge is not a subduction zone. That distinction is critical. Subduction zones are the places the world truly fears. The Japan Trench, the Cascadia Subduction Zone, the Chilean Trench, environments where one tectonic plate is diving beneath another, compressing stress over centuries, and then releasing it in catastrophic magnitude 8 or 9 megathrust earthquakes, capable of generating tsunamis that travel across entire ocean basins. This is not that. The ridge near Antarctica works on a fundamentally different principle. Here, the plates are not colliding. They are moving apart. The seafloor is being pulled in opposite directions. Magma rises from the mantle below to fill the gap, and new oceanic crust is formed in the process. This is called seafloor spreading, and it is the mechanism that has been slowly widening ocean basins for hundreds of millions of years. So if the plates are spreading apart, what causes the earthquakes? The process is not smooth, it never is. Along a mid-ocean ridge like this one, the ridge itself is broken into segments, and those segments are offset from one another by massive fracture zones and transform faults. At these transform fault boundaries, huge sections of ocean floor are not pulling apart, they are sliding sideways past each other. Stress accumulates along those locked fault zones over time. The rock bends and deforms, and eventually something gives. That release is the earthquake. And because the crust is thinner here than it is on a continental plate, and because the earthquakes occur at shallow depths, the energy reaches the surface of the ocean floor efficiently. That is why both events today registered at magnitude 6.0, despite being on a spreading ridge rather than a convergent one. The fact that two 6.0 earthquakes happened at the same spot within 10 minutes is the part that stands out. At a typical spreading ridge, stress is being constantly bled off in small increments as the plates drift apart and the magma intrudes below. Large concentrated releases like today's double event suggest that a particular segment of the fault system had been storing strain, locked against movement, and when it finally gave way, it did not resolve everything in a single rupture. A portion of the stress released in the first earthquake redistributed to the adjacent fault zone, which had its own loaded stress, and that triggered the second event almost immediately after. That is the mechanics of an earthquake doublet, and it is a clear signal that the ridge system in this section is not passively drifting. It is actively adjusting under significant tectonic load. The epicenter coordinates place both earthquakes at roughly 50 degrees south latitude, 139 degrees east longitude. That puts them in the cold ocean corridor between the southern tip of Australia and the Antarctic continent, a region sometimes described as the ocean gateway between two of Earth's most geologically distinct landmasses. This is not random geography. The entire southern boundary of the Indo-Australian plate runs through this part of the world. To the north, the Australian plate is colliding with the island arc systems of Indonesia and Papua New Guinea, producing some of the most intense seismic activity anywhere on Earth. To the northeast, it interacts with the Tonga-Kermadec system. one of the deepest subduction zones in existence. And to the south, it meets the Antarctic plate along these long underwater ridges, including the one that just produced today's double rupture. Looking at the broader pattern of recent seismic activity in this plate system makes the context even clearer. Aftershocks are still occurring in the Tonga region following a major earthquake there. Papua New Guinea recently recorded a magnitude 7+ event, and its aftershock sequence is still active. New Zealand and Fiji are also within this same tectonic neighborhood. Each of those events is its own separate story driven by local fault mechanics, and it would be a mistake to connect them all into a single unified narrative of planetary destabilization. That is not how plate tectonics works. But what these events collectively illustrate is that the entire Australian plate boundary system is in an active phase of stress release right now. And the southern boundary of that system, which is exactly where today's double earthquake happened, is very much participating. On the question of tsunami risk, a magnitude 6.0 earthquake on a mid-ocean spreading ridge does not carry the same tsunami threat profile as a major subduction event. The reason is the nature of the ground movement. In a subduction zone earthquake, a massive section of seafloor is thrust vertically upward or downward, displacing an enormous column of water above it, and that displacement is what generates a tsunami wave. On a spreading ridge, or along a transform fault, the dominant motion is horizontal, the plates sliding apart or past each other rather than vertical. There is less direct water displacement. No tsunami warning was issued for today's events, and that is consistent with the physical mechanics of what happened. The ocean near that ridge did not get pushed up or down violently enough to generate a wave system threatening to any coastline. What this event does represent is something different. It is a window into one of the most active geological systems on Earth, a system that operates largely out of sight beneath waters that see almost no human activity, along a ridge that most geography textbooks never even mention. The Western Indian Antarctic Ridge is part of the global mid-ocean ridge network, a system of underwater mountain ranges and rift valleys that circles the entire planet, roughly 65,000 kilometers in total length. It is the longest continuous geological structure on Earth. It is where new ocean floor is born. It is where the deep interior of the planet communicates with the surface. And today, in a particularly remote section of that system, it released 2 strong earthquakes in quick succession, suggesting that a meaningful amount of accumulated tectonic stress just found a path out through the seafloor. Antarctica itself tends to be framed entirely in terms of its ice sheet, how much is melting, how fast sea levels might rise, what the surface temperatures are doing. But the continent is geologically alive in ways that rarely get discussed. Underneath the surrounding ocean, the plate boundaries, fracture zones, underwater volcanic systems, and spreading ridges are continuously active. The geology does not pause because the surface is frozen. The same planetary engine that broke apart the ancient supercontinent Gondwana, that opened the Drake Passage, that separated Antarctica from Australia over tens of millions of years, that same engine is still running. Today's earthquake doublet on the Western Indian Antarctic Ridge is one small expression of that ongoing process. There is nothing here that signals an imminent catastrophe. No megathrust fault ruptured. No major population center felt anything. No tsunami is in motion. But 2 magnitude 6.0 earthquakes hitting the same underwater ridge segment within 10 minutes of each other. In a region that sits on the southern edge of one of the most tectonically complex plate systems on Earth is exactly the kind of event that warrants attention and documentation. The planet's crust is not static. It was never static. And every now and then, in places most people will never visit or even think about, it makes that fact very clear.